Hello once again. You have learned in your previous math subjects how to numerically compute for the variables in nonlinear equations, but in more complicated functions, the best by-hand approach is to take approximate roots. Learn about different approximation approaches here in numerical solutions to CE problems. Let's take a quick review about nonlinear equations before working on our approximation processes. Unlike our linear equations where you would find x and y into your equations, nonlinear equations such as polynomial equations would have x and y, also probably w, z, and other variables. For transcendental equations, exponential equations would be those which would be having x squared. This is going to be simply computed with your quadratic equation, but how about when you work with x to the fourth, x to the seventh, and so forth? Logarithmic equations would be those would be having your logarithms or your e's. Trigonometric equations with cosines and sines. And hyperbolic equations where you would find our equation y squared all over a squared less x squared all over b squared would be equal to 1. In approximating nonlinear equations, we are to assume that f of x is equal to 0. By function of x, we would mean y is equal to 0, or we are looking for the x-intercepts of the curve. For the first figure, having the curve with the function f of x, we are to arrive at 4 x-intercepts or 4 roots of x. For figure A, where the equation shows the quantity of 1 plus x squared, x-intercept or the function of x, wherein it would be equal to 0, would arrive at the vertex. For figure B, function of 1 plus x cubed, showing that curve, x-intercept would be at -1. There are two methods of finding roots. One is what we call as the bracketing method. By its name, we would have to work with the range that is included in the bracket. In this bracket, we would work with a lower limit and an upper limit. From this limit of values, we are going to iterate until we reach close to the root of the curve. How about for the open method? Instead of working with two values or two limits, the open method would only be asking for one initial guess. With different theories, just like tangent lines and secant lines, we can come up with a different point. And hopefully this point would be very close to the root of the curve. There are also non-numerical solutions in finding roots for nonlinear equations. One is the graphical method. A lot of drawbacks would be coming from its accuracy unless you are going to use a graphical calculator. Another method, which is non-numerical, would be what we say as incremental search method. This method would be purely guesses. So in case we do have our curve, and we are required to look for this root, since it's going to be purely guessing, probably you are going to work with from this point and take the value of your f sub x. Moving down would still be giving us negative. and finding that it's still going to be far from our root. Here, still negative, getting closer, but still negative. Take another point of x, working as negative, until such time that you would reach the range where later on it would turn as positive. With the change of signs, we can say that we are going to take these two as our upper and lower limits for this method. Let's consider this example. Determine the root of 4.15x squared minus 16x plus 8 using incremental search method, whereby we are required to look for 4 decimal places of the root. The first thing would be to guess a value of x and plug it into our f of x. Let's say that we would work with x is equal to 0. Placing our value of x into our f of x, we would have 4.15 times 0 squared minus 16 times 0 plus 8. These two would cancel out, and we have our f of x as 8. Now try another value. Let's say x is equal to 1. Our f of x, which is equal to 1, would give us 4.15 times 1 squared minus 16 times 1 plus 8. This would turn out as negative 3.85. In this case, since we have the signs reversed from positive to negative, then we are sure that our root of our function lies between 0 and 1. We can take x is equal to 0 as our lower limit, and x is equal to 1 would be our upper limit. After knowing that our upper and lower limits would show 0 and 1 for our root, then we can work with our smaller interval. Instead of having it as 1, let's try working with 0.2. So our second x or iteration would be 0.20. Plugging that value into our f of x, still with the same function, we would have our answer as 4.966. It would be a positive. So we would still have to continue until we would reach our negative sign. How about 0.40? If we plug 0.4 into the function, we would get positive 2.264. Still a positive. So moving further, let's take 0.60. At this point, plug 0.60 into the function, then we have negative 0.106. So we can say that we can have our smaller range of the root of x as 0.4 for the lower limit and 0.6 for the upper limit. Now that we have reduced our range of our limits from 1 and 0 to 0.4 until 0.6, then we can look for another subinterval. This time we are going to use 0.05. So from 0.4, we can work with 0.45. And again, plugging our value of x of 0.45 into the function, and that would be 4.15 with 0.45 squared less 16 of 0.45 plus 8, we would get positive 1.640375. This is still a positive, so we move on to the next. With the interval of 0.05, then we can take 0.50. Plugging 0.50 into our function, we get positive 1.0375. Still a positive, so we continue with 0.55. This would give us 0.455375. Now we can see that we are onto the upper level. So we are sure that the root of the curve would turn out from 0.55 to 0.60. Next step. Knowing that our root lies between 0.55 to 0.6, then we can work on with our next subinterval. So let's have our subinterval 3 as 0.01, which means that we are going to have from 0.55 would be 0.56. And again, placing it into our function, so that would be 4.15 times 0.56 squared less 16 times 0.56 plus 8. Then we arrive at 0.34144. Still a positive. So we continue with 0.57. By plugging in our value into the function, then we get still a positive 0.228335. And continuing with 0.58, f of x would turn out as 0.11606, but is still a positive. And lastly, we have 0.59. This would turn out as 0.004615. And again, the bracket would still be showing that we work with the higher values. Now we are down with finding the root of our curve to 0.59 and 0.60. However, we are required to have 4 decimal places, so let's continue with our next subinterval of 0.001. Starting, we get 0.591, and placing this into our function, which would be 4.15 times 0.591. That would be squared less 16 of 0.591 plus 8. And we get negative 0.00648. With this first try, we would be sure that we have our next decimal place coming from 0.59. Now we know that our root lies within 0.59 and 0.591. So we work with our last interval of 0.0001 to have 4 decimal places. Let's start with 0.5901 by plugging it into our function, thus having 4.15 of 0.5901 squared less 16 of 0.5901 plus 8, we get positive 0.003505. Still a positive. So let's continue with 0.5902. From this point, we would still have a positive f of x, giving us 0.002395. So we keep moving on to the next. And that would be 0.5903, and we get 0.001284. How about having one subinterval added to 0.5903? We still have a positive value of 0.000174. So keep going. Take 5905. We'd get this time a negative value of 0.00094. Now we can stop our iteration. How are we going to find our root in 4 decimal places for the function? We are going to compare our f of x, which would be closer to 0. At this point, we can say that that value of f of x coming from 0.5904 would be closer. So our value, the root of x, would be taken as 0.5904. You have observed in the incremental search method that we would need to work on so many different intervals in order for us to get the root of a certain function. In bisection method, it states that we are going to get the mid value, and from there we would have to move going to the lower limit or to the upper limit, and it's going to save us some time. By taking our mid value, that would be just like the average of the two limits, that would be a plus b all over 2. So let's check on this example. Determine the root of the function of x given as negative 0.60 of x squared plus 2.4x plus 5.5 with bisection method. With the same procedure, we are going to have our initial guess. Let's say x is equal to 0. By plugging this value into the function, we get f of 0 is equal to negative 0.6 multiplied by 0 squared plus 2.4 times 0 plus 5.5. And since the first and the second terms would be 0, then with x of x is equal to 0, we have 5.5. Let's check on if x is equal to 1. For the function, we would get negative 0.6 of 1. That would be squared plus 2.4 multiplied by 1 plus 5.5. We get 7.38. Notice how our values for f of x increase as we increase x. That would mean that probably we are supposed to work on x is equal to negative 1. So let's try x is equal to negative 1 this time. Again, take our f of negative 1. So negative 0.6 times negative 1 squared plus 2.4 times negative 1 plus 5.5. Our answer is still a positive, but note that it's reaching or closer to 0. So let's move ahead and get x is equal to negative 2. So the function of negative 2 would give us negative 0.6 times negative 2 squared plus 2.4 that would be multiplied by negative 2, and lastly, plus 5.5. This would give us negative 1.86. And finally, we had a change in signs, which would mean that our root would be taken within x is equal to negative 1 and negative 2. Let's get our lower limit, which is equal to negative 2. This would be our value for a, and the upper limit, taken as negative 1, would be our value for b. Now let's continue our bisection method using a table. So we said that the lower limit would be negative 2 and the upper limit would be negative 1. From our definition earlier, we would have the mid-value for c, which would be taken as the average of a plus b, or that would be everything divided by 2. So, for the first iteration, we can have c equal to negative 2 and negative 1 divided by 2, which would give us negative 1.5. Plug this value into our equation, and we would get positive 0.43. The positive sign would mean that we would need to reduce the upper limit. In order for you not to forget, positive sign of FC would be changing the upper limit, and the negative sign coming from f of c would have to change the lower limit. What about the last column stating b take away a? This would mean that we would have to check on when to stop our iteration. Observe that from our problem, it didn't ask us or not requiring any of our decimal places, which would mean that we are going to work with this computation in order for us to know when to stop. So when are we going to stop iterating using b minus a? It is when the value for b minus a would be less than 0.001. So let's continue with our iteration. Negative 2 minus 1 would give us 1. So it's still a long way ahead in order for us to stop iterating. Check on our value for f sub c. It is given as positive, which would mean that we are to change the upper limit. Our lower limit would remain negative 2, and the upper limit is then replaced by negative 1.5. Knowing these two values, we can take their average, negative 2 minus 1.5, all over 2 would give us negative 1.75. And plug this value in order for us to get our f of c, which would give us this time a negative value, 0.6775. b take away a would still be 0.5. Again, take note of the sign of f sub c. It gives us a negative value, which means that we are going to change this time the lower limit. The lower limit is replaced by 1.75, while the upper limit would remain 1.5. With these two known, we can get their average, which is 1.625. And by plugging this value into our function, we arrive at negative 0.11438. b minus a is 0.25. Again, check for the sign. It's another negative, which means that c would replace our lower limit, and that would be 1.625, while the upper limit would remain as 1.5. So take their average, which is going to be 1.5625. Plug this value into our function. This time we get positive 0.160156. B minus A is taken as 0.125. Again, observe the sign. It's a positive this time, which would mean that we are going to replace the upper limit. Lower limit would remain the same, negative 1.625. The upper limit is then taken as negative 1.5625. And taking their average, we arrive at 1.59375. If we are going to plug this value into the function, we get again a positive value, 0.023477, and B minus A is taken as 0.0625. Still a long way to go until we reach 0.001. So again, check that we have a positive function of C, which would mean that we are going to change or replace the upper limit. The lower limit would still be 1.625. The upper limit is then taken as negative 1.59375. Then take their average. It would be negative 1.60938. And with this value, we get f of C, which is negative 0.0453. B less A is 0.03125. So again, we get back to the negative sign, which means that we would need to change or replace our lower limit with C. That would be 1.60938. The upper limit would still be 1.59375. Taking their average, we get 1.60157. And placing this value into the function, we arrive at again a negative value of 0.01089. Take B minus A, we have 0.01563. This time we are closer to 0.001, but we still need some more iterations. Take note again that we have a negative sign here, which we are going to replace our lower limit. Then we get 1.60157, the new value for C. Our upper limit would still remain the same as 1.59375. Taking their average, we would get 1.59766. If we plug this value into the f of C, we have a positive value, 0.006293. B take away A would be taken as 0.00782, very near 0.001. This is a positive, so we have to maintain 1.60157, but change our upper limit into 1.59766. If we take their average, we get 1.59962. And the function of C resulting would be coming out as negative 0.00231. B take away A is 0.00391. We replace the lower limit. Our new lower limit would be 1.59962. The upper limit would remain the same as 1.59766. Take their average. We have negative 1.59864. And if we plug in this value, we would arrive at f of c as positive 0.001983. Our b minus a is taken as 0.00196. Probably the last iteration until we reach a number less than 0.001. So take the positive sign, which would mean that the lower limit would be remaining as 1.59962, but the upper limit would then be replaced with 1.59864. Let's check b minus a. We get 0.00098. This is definitely smaller than 0.001. So we can say that the answer or the root of x would be taken as that of the upper limit, or that is negative 1.59844. The root of x is then negative 1.59844. The next bracketing method is regular falsi or false position method. In this approach, instead of using random intervals or the average of the limits, linear interpolation is used. Thus, the computation of the new value of x is through the formula shown. By computing the same example as bisection methods earlier, we recall that with a, which is equal to negative 2, our f of a came out as negative 1.86. b was taken as negative 1, and f of b is positive 2.42. The same procedure would be followed by regular falsi method, that from bisection method. The only difference is this time we are supposed to place the columns for the functions of a and functions of b as they are taken or considered into our formula for computing c, which is given as c is equal to a times the function of b minus b times the function of a all over function of b less the function of a. So let's proceed with our zero iteration. If we have a as negative 2 and b as negative 1, using our formula, we can compute for c, which would turn out as negative 1.56542. Again, if we plug this value into our function, we get 0.147432. Notice that this is a positive, which would mean that we are going to maintain our value for a, which is negative 2, but b would be replaced by c, which is negative 1.56542. Thus, we can still say that a positive f sub c would change the upper limit, and a negative f of c would be replacing the lower limit. With negative 2 as a, our f of a would remain as negative 1.86. Our f of b would be from f of c taken as 1 or 0.147432. Now plug a and b, fa and fb into c, and we get negative 1.59734. With this value, our f of c would turn out as positive 0.007711. Note that what we have with f of c is still a positive, which means that our lower limit negative 2 would remain, but the upper limit would change into 1.59734, which is negative. F of a would still be negative 1.86, but f of b would be taken as 0.007711. Then do the same thing. Take the value of c, which would turn out as negative 1.599. And placing this into the function, we arrive at again a positive value 0004. Since it is a positive, our lower limit would still be negative 2, but the upper limit would then take negative 1.599 as its new value. So negative 1.86 would remain the same, but f of b would already be 0.0004. Taking the value of c, we would arrive negative 1.59909. And its function would turn out as 40207. If we try the next iteration, that would be still taking negative 2 as our lower limit, but the upper limit taken as negative 0.59909, maintaining our f of a, but our f of b would be taken as 40207. Then f of c would still be taken as 1.59909 negative, with its f of c as 0.50108. Note that we are not changing our value for for c anymore, and our f sub c has almost like taken the 6th decimal into 0. So we can say that our value for x is taken in this method as negative 1.59909. The discrepancy from the root of x taken with bisection method is probably the rounding off of our decimal values.